Okay, so what we're going to look at is how we can solve for the mass of a planet using the orbital radius and orbital diameter of an orbiting body, like a moon or a planet around the sun. So the formula that we're given a couple of formulas, and one of them says m1 plus m2. Now, you may notice that in another formula, they just simplify it to one mass. And that's because if the first mass that we're dealing with is the mass of the sun, for instance, then the mass of the planet is going to be so small in comparison that it essentially is omitted. So then what we get is 4 pi squared over g, which is the gravitational constant, times the orbital radius cubed over the orbital period squared. And you'll notice that sometimes that orbital period is given the symbol t instead, and sometimes the radius is given a small r, but either way it's the same. Now, if you looked at sample problem 9 in the resource page, it tells you that Jupiter's moon, Io, has an orbital radius, so they tell you the orbital radius is 4.216 times 10 to the 8 meters, and they tell you that it orbits around Jupiter in a time, or the orbital period, of 1.769 days. So if we look at the formula and then we look at the values that were given, we can see what we have so far and what we still need to sort out. So we have R, check. We have P, check. Now we know G is a constant. So we know that G is always 6.67 times 10 to the negative 11. Now, when we're looking at the units of this universal gravitation constant, one of the things to note is that all of the other units that we're dealing with have to be SI units, and days are not the SI unit for time. So in order to convert this to the SI unit, which is seconds, we're going to multiply by 24 hours in a day, 60 minutes in an hour, and 60 seconds in a minute. And then all the units will cancel, days over days, hours over hours, minutes over minutes, and we'll be left with seconds. And so pause for a second to plug that in, 1.769 times 24 times 60 times 60, and see what you get. So if you plugged it in, you should find that you get 152,842 seconds. Technically, we shouldn't keep all those digits though, and if we're rounding, remember, if we're going to put it in scientific notation, remember that we're going to go count how many decimals we move it, 1, 2, 3, 4, 5, so 1.528, 4 digits, 1, 2, 3, 4, same as our original value, times 10 to the 5 seconds. So that's the time that we're actually going to use to solve the question. So now we have all the values we need, and we just need to plug them in. So to find the mass, we're going to do 4 pi squared, and pi you don't want to write the value, you want to use the pi button on your calculator, over 6.67 times 10 to the negative 11 times 4.216 times 10 to the 8, which is our orbital radius that we were given, to the power of 3. Over, we're going to take our orbital period, but in seconds, the SI unit, 1.528 times 10 to the 5 squared. Okay? So pause for a moment, find out what this cubed and that squared and this 4 pi squared come to before you continue on. So hopefully what you found is that 4 pi squared comes to 39.478. You can keep more decimals in this, obviously, because pi has an infinite number of digits, but 5 digits is probably tons, over 6.7 times 10 to the negative 11. Now, 4.216 times 10 to the 8 cubed comes to 7.494 times 10 to the 25. And 1.528 times 10 to the 5 squared comes to 2.336 times 10 to the 10 Now again, pause for a moment. If you hadn't gotten this far, take these values, plug these in to figure out what the right bracket comes to and also what the left bracket comes to. So hopefully you found that 5.9, this comes to 5.919 times 10 to the 11. We're dividing a moderate number by an extremely small number, so we end up, sorry, there's no negative there, getting a large number. And on the other side, we end up getting, actually, I think what I did is I plugged it all in at once. Okay, so our final answer, so this is, I've just plugged it in all at once. So I did this, I just left this like this and plugged these three all in at once. You want to do whatever you can to save the number of steps you have to write in. So our final answer should come to 1.899 times 10 to the 27 if we're maintaining these 4 digits. And our unit is going to be in kilograms. Now, if you Google the mass of Jupiter, so we did plug this all in, and we get 1.899 times 10 to the 27 kilograms. If you Google the mass of Jupiter, this is really close. So it's an awesome calculation that lets us predict the masses of all these bodies. The really neat thing to note too is that it's this exact same method that's been used to calculate the masses of all the objects in the solar system as well as masses of stars. Because we can look at using parallax or magnitude to find the distance or the orbital radius to these objects. And we can figure out using their distance, we can figure out the distance between 2 orbiting objects. So say we had 2 binary stars orbiting around each other, we can use parallax to figure out this distance, and then we can use that to determine their mass. So they can figure out the relative mass of some of these very distant objects using this exact same relationship. A little bit more to it, but same basic principle.